In section 4.9 here, we're going to talk about differentials. And the four main points we're going to cover in this section are understanding the concept of a tangent line approximation. We're going to compare the value of the differential, dy, with the actual change in the y variable, delta y. We're going to estimate a propagated error using a differential, and find the differential of a function using differentiation formulas. Okay, tangent line approximations. In a previous section, there was Newton's method, and that was an example of using a tangent line to a graph to approximate the graph. It was an estimation method. In this section, you're going to study other situations in which the graph of a function can be approximated by a straight line. To begin, consider a function f that is differentiable at some point c. The equation for the tangent line at this point, f of c, that's our x and y coordinate, is given by, we're familiar with y minus y sub 1 equals m times x minus x sub 1. Well, here it is with this calculus notation. Y minus y sub 1 is y minus f of c, and that is equal to the derivative at the point. Remember, the derivative is just a slope. The derivative at point c times the quantity x minus c. And if we add this negative f of c to both sides, we get y equals f of c plus the derivative at point c times x minus c. And this is called the tangent line approximation, or linear approximation of f at point c. Because c is constant, y is a linear function of x. Moreover, by restricting the values of x to those sufficiently close to the point c, the values of y can be used as approximation, and we can get any desired degree of accuracy that we want of the values of the function f. In other words, as x approaches c, the limit of y is f of c. And we'll check this out here in example 1. Find the tangent line approximation of the function f of x is 1 plus sine x at the point 0, 1. Then use a table to compare the y values of the linear function with those of the function f of x on an open interval containing that point x is 0. So the first thing we need here is to come up with the tangent line of this curve at the point 0, 1. So our function is f of x equals 1 plus sine x. So to come up with our tangent line at that point, of course, the first thing we're going to have to do is derive it, f prime of x. Well, the 1 is a constant, it derives away to nothing. The derivative of sine is cosine. Oh, that was easy enough. So we need the equation of the tangent line at this point. The equation of the tangent line of f at point 0, 1 is, let me even write that out, equation of tangent line at the point 0, 1. That's what we're finding right now. And again, we're familiar with y minus y sub 1 equals m quantity x minus x sub 1. Well, now it's going to be y minus f of 0 is equal to the derivative's value at point 0 times the quantity x minus 0. So, y minus. What is f of 0? Well, if I plug 0 into the original function, I'm going to get 1 plus the sine of 0. The sine of 0 is 0, so the value there is 1. Equals the derivative at point 0. Well, if I go to the derivative here is cosine x, the derivative at point 0 would be the cosine of 0, and the cosine at 0 is 1. And then we have still our point x minus 0. So we have y minus 1 equals 1 times the quantity x minus 0. Well, x minus 0 is just x, times 1 is x. And to get y by itself, we add 1 to both sides. Y equals x plus 1. So our tangent line is y equals x plus 1. So what can we get rid of? Let's get rid of this. And now what we're asked to do next is use a table to compare the y values of the linear function with those of the curve, the derivative sine x, on the open interval containing x. So here we're going to go to the TI-89, the calculator. Our original function is 1 plus sine x. We can put that in the y editor and go to the table. We can also plug the tangent line that we found, y equals 1 plus x, into the y editor. And we're going to plug in these x values and compare the outputs that come out. Well, let's start at the point of interest. We were interested in the point 0, 1. So if I plug 0 into the original function, f of x, I get an output of 1. And if I plug 0 into this tangent line approximation, I get the same value of 1. You know, here at this point, they are identical. And we're going to see as we drift away from that point, we're going to get an error between the two, and it's going to grow the farther away we get from 0. If we plug 0.01 into the original equation, we get 1.0099998. And if we plug that same value of 1 into our tangent line approximation, we get 1.01. Very, very close. You know, our value at 0 was identical. As we drifted 0.01 away from that value of 0, we're still pretty close to being equal. If we plug in 0.1, our original function gives us a value of 1.0998. And the tangent line gives us 1.1. Again, they are still pretty close, but the error is growing between them. If we plug in a half, 0.5, our original function gives us a value of 1.479. The tangent line approximation of 1.5. Again, as we get farther away from that tangent line, or that point of tangency, the error between the two, between the original function and our tangent line, is growing. And the same holds true as we head in the negative direction. At negative 0.01, our original function gives us 0.99, and then it has 4 zeros and a 2. 0, 0, 0, 0, 2. The tangent line approximation just gives us the 0.99. At negative 0.01, our original function is 0.9002. Our tangent line approximation is 0.9. And at negative a half, the original function is 0.521. And the tangent line approximation is 0.5. We can see the distance between the f of x and our tangent line is growing. It's getting a bigger and bigger gap between them as we get farther and farther away from our point of tangency. And this I like to look at also graphically. Here's the graph of what's going on. The original function, 1 plus sine x, is the sine wave moved up 1 unit. So our sine wave comes up and then starts to head back down. We found the tangent line at this point. So we used that point, we found the slope there and ran a tangent line and found this. At the point x is 0, they're identical, they touch each other. As we start to move away on the x-axis, we can see there's a little gap here, and the gap grows the farther away we get. And the same thing to the negative side. As we're real close to that point, x is 0, the lines almost coincide, but as we move away, this gap in here begins to grow. Now, differentials. When the tangent line to the graph of a function at this point c comma f of c, we have our tangent line y equals f of c plus the derivative at the point times x minus c. This tangent line is used as an approximation of the graph of f. The quantity x minus c, right here, is called the change in x and is denoted by delta x, as shown in figure 366. When delta x is small, the change in y, denoted by delta y, can be approximated as shown. So delta y is f of c plus delta x minus f of c. This is the actual change in y. How much did y really change? And that is approximate to, or pretty close to, the derivative at point c times delta x. For such an approximation, the quantity delta x is usually denoted by dx and is called the differential at x. The expression f prime of x dx is denoted by dy and is called the differential of y. And let's check that out on the diagram. So here we have the curve is our function f, and the blue line is our tangent line approximation. Here at point C is our point of tangency. If we move along the x-axis some amount is delta x. So we've moved this amount delta x to the right on the x-axis to this point C plus whatever delta x was. Now if we stick to the curve, if I pick this next point here on the curve itself, on the curve f, this height, we have changed our x coordinate by delta x. So we've changed on the curve f of c plus delta x. That is our actual change, or the actual change on the curve. This tangent line approximation, again this light blue line is our tangent line. When we move that same amount on the x-axis, we again move some amount delta x, and we move from this point and we stay on the tangent line. Well, this height is f of c, our original height of our point of tangency, and then we move up this little bit more to get onto the tangent line. And you know this little chunk is the derivative at point c times delta x. That out of the way there. So delta y is the true change in the curve, the true change on the function, on the curve. C-U-R-V-E. Down here on the x-axis, delta x is exactly equal to dx. Those are exactly the same. But delta y is not the same as dy. And let's come back to the picture here. Let's see if we can make this a little more clear. Delta y is the true change on the curve. So we were at this point on the curve, or at this height on the y-axis, and then after we added delta x to the x-axis, we now wound up here. So the gap between this y value and this y value is delta y. And actually, yeah, it's right here. You know, this jump is the true change on the curve. We were on the curve, we added some delta x to it, we were still on the curve. That is our delta y, or the true change on the curve. This differential is, again, the tangent line approximation. So here we were, again, on the original curve, but now we're going to go off onto this tangent line approximation. This height, how much did we change from the curve onto the tangent line approximation? That is our differential, f prime of c delta x. And you can see here's the error that we saw in the table. The difference between being on the actual curve and being on the tangent line after we have moved some amount on the x-axis, some delta x. So our definition of differentials: let y equal f of x represent a function that's differentiable on an open interval containing point x. The differential of x, denoted dx, is any non-zero real number. The differential of y, denoted by dy, is the derivative at point x times dx. In many types of applications, the differential of y can be used as an approximation of the change in y. That is, delta y and dy are pretty darn close. They're approximately the same. Or delta y is approximately the derivative at point x times dx. Here in example 2, we're going to compare delta y with dy. Again, remember, delta y is the true change in the curve. Dy is our approximation of the change on the y-axis. So let's do this as a side-by-side. First here it says let y equal x squared. Find dy when x is 1 and dx is 0.01. And then we're going to compare it with the true change, delta y. So our tangent line approximation, to solve for dy, we're going to take our original function, y equals x squared, and we're going to derive it. The derivative of y with respect to x is going to equal 2x. And we're finding dy, so let's multiply both sides by dx. dy equals 2x dx. And we're interested at the time when x is 1 and dx is 0.01. So dy equals, well, x is 1, so 2 times 1 is 2, times dx, 0.01. So dy equals 0.02. This is our differential for y. Differential for y. Now let's compare that to the true change in the curve. You know, this again is our approximation. Well, delta y, the true change, is equal to f of x plus delta x minus the original f of x. So delta y equals, well, our original x value was 1, and we added 0.01 to it. So this is going to be f of 1 plus 0.01 minus f of 1. And again, our x value here is x is 1. So delta y equals f of 1.01, f of 1.01 minus f of 1. And our function here was x squared. So it's just a simple squaring function. Delta y is going to equal 1.01 squared minus 1 squared. And if we punch that in the calculator, we get delta y is equal to 0.0201. And if we compare the two, 0.02 to 0.0201, you know, we're pretty darn close. The difference between them is a 10,000th, 0.0001. We can see that they are pretty darn close. And let's look at this graphically. Oop, a little too big. So here's our squared function. Y equals x squared is the black dark line. The point here is 1, 1. When we changed our x coordinate by delta x, you know, here we jumped over from the point delta x. How much did we change on the true curve? You know, on the curve, we're right here. So this is our delta y, the true change. We moved on the x-axis. How far did we change on the y-axis? For the differential, you know, we moved the same amount, delta x, but when we went up, we hit the tangent line first. And that is our dy, our differential. You know, so there is this gap. That was the gap we found of 0.0001. Delta y and dy are not the same thing. They're pretty close if we stay close on the x-axis. Error propagation. Physicists and engineers tend to make liberal use of the approximation of delta y by dy. One way this occurs in practice is for the estimation of errors propagated by physical measuring devices. For example, if you let x represent the measured value of a variable, and let x plus delta x represent the exact value, then delta x is the error in measurement. Finally, if the measured value of x is used to compute another value, f of x, then the difference between the two, x plus delta x and f of x, is the propagated error. And here we have our f of x plus delta x, that's the exact value, and delta x is the measurement error. Minus the measured value, the true value, we get our propagated error. And this will be cleared up a little bit here in example 3. Estimation of error. The measured radius of a ball bearing is 0.7 inches. So here in a pair of mics we got a ball bearing 0.7 inches as shown in the figure. If the measurement is correct within 0.01 inch estimate the propagated error in the volume of the ball bearing. So, for a sphere, we have volume equals 4/3 pi r cubed. Our radius in this problem is 0.7, and our delta r. Our delta r, our how correct are we in our measurement? We're within 0.01. So we could think about it as, the error there is less than 0.01, greater than negative 0.01. We're somewhere in there, plus or minus 0.01 is the correctness of our measurement. To approximate the error in the volume, we're going to have to differentiate v. So the derivative of v with respect to r, dv dr, would be 4 pi r squared. And since delta v is approximately the same as dv, we can say that this is 4 pi r squared dr. 4 pi r squared dr. And now we can just plug in some stuff from our given setup to the problem. So we have 4 pi. Our radius was 0.7. So we're going to have 0.7 squared for the radius squared. And then dr was within 0.01 inches. So times, and think about it as plus or minus 0.01. Well, if we work this out on the calculator, 4 times pi times that radius squared times 0.01, we're going to get approximately plus or minus 0.06158 inches cubed, because again we're talking about volume. So what we said here is, we're measuring the diameter or the radius of this ball bearing, and we might be a little bit off. Our measurement might be a tiny bit wrong. How much is that going to affect the volume of the sphere? Well, if our radius measurement is off 0.01, or it's to the negative side, negative 0.01, the most it's going to mess up our volume is this many inches cubed. Now, is that a large amount of error or a small amount of error? Well, it's relative to the problem. And we're going to compare now. Is that a big error? Is it a small error? We're going to compare dv and v. We're going to make a ratio out of dv and v. So we're going to do dv as the numerator, v as the denominator, and see what, as a percentage, how much is that error. So our dv to volume, our dv was 4 pi r squared dr over the original 4/3 pi r to the third. And we're going to get some stuff cancels here. The pi's will cancel out. This r squared will take out all but one of these r's. If we invert and multiply here, 4 divided by 4/3 is going to be 3. So up top we'll have a 3. So we have 3 dr over r. Let's see here. Well, the numerator is 3. The r was 0.7, and the dr was our 0.01, plus or minus, the amount of error we might have, plus or minus 0.01. And if we plug that in the calculator, we get approximately plus or minus 0.0429 as a decimal. And if we want to change that into a percent, we move that decimal over 2 spots. We get plus or minus 4.29%. In the industry or whatever you're working with, is that an acceptable error? Just depends. 4.29% error in volume based on, maybe our radius measurement was a little bit off.